Hi, my name's Tim DuBois. I'm a senior scientific software engineer at Servest. I'd like to introduce you to Agents.jl. It's a project that I've been working with for about 2 years, along with a couple of my co-authors. And this is an animation done in Agents. It's showing you an SIR model. You might be quite familiar with these based on the past couple of years of pandemic chaos. It's showing some agents that have effectively become infected and others, that's in red, and others who are hiding in place in black, and some who have recovered in green. So agent-based models, what do they do? Well, effectively they're a paradigm. They're a way to look at a certain class of problems and to be able to solve them based on relatively simple ideas. So it's a bottom-up approach. And generally what you do is you find the sort of fundamental building blocks of what your problem is. So we call them agents. So these could be something simple like an ant or a car, or perhaps even a molecule. And using certain rules that are set upon those agents and certain environmental properties, you can go ahead and study various different emergent properties, generally in sort of the complex adaptive systems space. But that's not the only place we can look at things with agents or with ABMs in general. There's a lot of behavior and decision-making processes that are studied here. So a lot of social science, crowd dynamics, various other sort of socioeconomical problems. But then as well in the physical sciences, there's a lot of biological processes and other sort of chemical reactions that you cannot simulate because you don't have a closed form solution. And so these are the things that agents and agent-based models can actually help you with in your research. Agents.jl itself is part of the Julia Dynamics community of models, and these are the main contributors to the project. It's primarily at the moment myself and George Datseries. Ali Vahadi has been on the team for quite some time. He was the original author. And we have a Google Scholar of Code student now, Ayush. And a number of different contributors have helped out with various aspects of the project along the way. We also have a paper coming out very soon, hopefully, but unfortunately it wasn't available for JuliaCon this year. So I'd like to sort of give you a very quick overview of what we think the philosophy of Agents.jl has been, and that is 4 key ingredients. It needs to be simple, it needs to be performant, interactive, and integrated. And I'm going to explore these different aspects over the next couple of minutes. So first of all, I want to start with an example. We won't have time to go through all of the details of how you actually build an agent-based model, but we do have extensive documentation that you can follow. This is one of those examples. So essentially what we're trying to do here is we're trying to model a zombie outbreak. So we have one infected agent on some type of map somewhere, and that zombie will go ahead and affect as many people as it can. So ultimately, all we need to do that is get agents on board, so load it up, and create an agent type. So this little macro here sorts out all of the other sort of a few other properties that you need to make an agent in general, which is basically in this instance a ID and a position. And then any properties that you would like, you can build here. So we want to know whether this zombie is essentially a person or an infected agent. We need to provide a space. There are a number of different spaces you can use here, although the one that we're going to use is the OpenStreetMap type of space. So this is just one function that you effectively generate the entire system with. You create a model which you can give this zombie structure to, as well as an OpenStreetMap type of space. And then this loop here will generate about 100, or exactly 100 people. So we identify a person with this false flag, they're not infected. And here are a couple of different examples of how you can actually initialize a person's position on this particular space. So a random position will give you at an intersection, or a random road position will of course give you something directly on a road. And then in this space we can plan a route. So from this start and finish position, we create a route for this particular individual, and then we add this agent directly to the model. The last person we have is essentially patient 0, so the zombie that we want to start infecting people with. And we've given 2 other sort of examples on how you can add agents here. That's effectively via a direct latitude and longitude coordinate. So this gives us the entire model and the set of agents that we will require to build this particular example. The last thing we need to do is provide an agent step, and that is how the agents move throughout this space. And so generally what we're doing here is for each agent, they will move along the route that we provided previously. And if they've stopped, just give them a random chance of actually starting again, right? So make it like they're done an errand or something like this. And then the last thing we do is we check if we have an infected agent. That could be our first initial agent or somebody who's been infected subsequently, and then check everywhere around them to see if you have people there, and if you do, infect them. And this gives you the entire machinery to generate a graph like this, which effectively, as you can see, you have these agents running around in black, and green are the zombies, and as they continue, this just spreads. Now, this example is relatively straightforward in terms of the conceptual process, and also relatively straightforward in terms of how you output this information. But what this shows you is the direct simplicity of Agents.jl, and that's actually sort of saying quite a lot when you compare this to other agent-based model frameworks that are currently available, at least the open source ones. So this is what I'd like to get into now. For one, this OpenStreetMap space is essentially the only, Agents.jl is the only framework that actually has this capacity as far as we're aware. So we're showing examples here that are simple for agents, but are actually highly complicated for other frameworks that we've compared agents to. And so this is what I'd like to move on to this performance. Now I'm just going to swap myself around here so we can actually see this table. And this is a table that we put together that compares 3 other ABM frameworks that exist and are currently in very active development. So Mesa, which is a Python implementation, which is where agents actually came from initially. It was the original sort of version 1 of agents was very similar to Mesa. It's now changed dramatically over the subsequent versions, but ultimately that's where agents was born. NetLogo is a very popular agent-based model framework. It's written in Java and has been around for decades, and similar to Mason, it's also a Java-based system that has different sort of requirements than NetLogo. But ultimately, all of these frameworks, those 2 frameworks have been around for quite some time. Mesa is relatively new. Agents is only about a year or 2 old. And so what this shows is 4 different colors. We define the red is basically saying this is not worthy because it doesn't actually exist. And we have yellow being, well, it's okay. I mean, it works. Green is, well, it's pretty good. And blue is best in class. Now, you can fairly straightforwardly see that we've listed agents as first in class for everything here. And these are 4 different example models that we have tried to showcase the greatest breadth of what ABMs can do for you. So there's a couple of different space models. So continuous and grid in these definitions here are actually talking about different spaces that exist in agent-based models. They're fairly standard. And these different systems are primarily showing different things that an agent-based model needs to do. So a big thing, for example, is looking for nearest neighbors over a certain radius. Because the system is dynamic in general, you can't use things like KDE trees to actually improve performance in this sort of space. And so it means that your nearest neighbor searching needs to be quite under wraps. And so generally what we're seeing here is a major performance boost for agents in general, alongside its simplicity. So let me explain this graph a little bit, this table a little bit to you. Lock means lines of code. And so in this particular example, which is flocking, it's birds flying around and flocking together. Agents can implement the very small, precise grammar that is used to talk about what flocking is. And it can do that in 62 lines of code. Now, there aren't any other framework that can actually match this, for example. And so NetLogo is close with AD2. But the problem with NetLogo is that it has this bracketed version here, number set here, which is ultimately because NetLogo's GUI has a lot of its setup inside the GUI. And so when it saves its files to disk, all of the initialization parameters are sitting within that aspect of the program. So the 82 lines of code is implementation, but it's not setup. And the values for all of the other tools that we're comparing here has setup as well as implementation. So this is not a true representation of 82 is not a true representation of what NetLogo is actually requiring here. And so that means that we're beating all of these tools in terms of how many lines of code you need to write to be able to express yourself enough to generate these kind of models. And this is across the board, right? So for every single one of these models, we have the smallest lines of code. What about performance? So performance here is normalized against agents. So however long it takes on any machine at all, it will take 1 unit of agent time. And so you can see here that for flocking, for example, Mesa takes almost 27 times longer. And the only really decent response that we got out of this performance metric was Mesa in this instance, which we can still beat, but not by much. But if you take a look at the rest of the table, like, I mean, when you've got an 8 times speed up in most places, that's usually a call for celebration. And we've said in this table that that's actually pretty good in compared to some other aspects of the table, like 125 times speed up we can get for this forest fire implementation. So when you expand these kind of models to incredibly large spaces and thousands and thousands of agents, especially because you have these interactions, a lot of this sort of stuff can't be inherently parallelized in many aspects of agent-based modeling. It's very dependent on what the agents, of what your individual model can do. This generally needs to be only sort of dumb parallelized if you need to run multiple different models. You generally need to run this in sort of a single core. And so when you're expanding to such large properties, these can take days, some of these runs. And so 125 times speed up in that particular instance is just a no-brainer that you want to use a performant framework. So what else? Well, we have interactivity, and this is something that we pride ourselves on a lot. So I'm just going to move myself across here again and show you an interactive system that we have working. This is a diffusion aggregation simulation that tries to build fractals, basically. And this is a Mackie interactivity based sort of platform that we have provided as a part of the interactive dynamics library. And that showcases and works for all of the Julia Dynamics organizations projects. And so what I can do here is I can show you, I can press this run button, and we're just seeing that with these various different sliders here, that the fractal is essentially growing as we have some type of pull to the center, some wobbles and various sort of aspects. But we can change what this sort of does. So perhaps we want to increase how much clockwise fraction there is. And then we update the system, and then we run it again. And maybe we sort of speed this up a bit. And then we can see that we've got things coming in left and right. And so what this allows you to do is you can change essentially anything you want in here, update the system, and it's just going to change the properties of the entire process. So you can keep doing this as much as you want. Then maybe we reset and we start again. Increase the speed, we update. And so this gives you complete control over every single property that you have within your model straight away. And so this gives you, excellent ability to parameterize your model if you don't know what's going on. Figuring out the best way to interact with your data is really, really helpful in that regard. Okay, so the final thing I'd like to talk about is integration. And this is a big aspect of how we have designed agents. So a lot of other ABM frameworks on the market have a lot of packages and extensions and the ability to add your own sort of code into the framework, so long as you write an extension directly for that framework. It's not something that we think that we should have to do in the Julia ecosystem. So this particular example here is showing one of the things that Mason does as their main example, where they have a grid space on the ground, and they have a bunch of school children going to play. They're not allowed to go to the edge of the fence. They've got to stay close to the teacher who's in the center. But then they have a couple of requirements. They have a social network, which we integrate with light graphs to provide. And the social network basically has a few properties. One is that there's the agents in general have the ability to sort of be brave and go further out, but they're still a bit scared and they go towards the teacher as well. So they have this attraction towards the teacher in some sense, weaker for some, stronger for others. Then we have people who like each other and people who dislike each other. And so the people who dislike each other need to run away from those who they don't like and find their friends. So this guy, for example, is running to find this one, and these pairs are very close already. So this interaction is, integration is one of the things that we really celebrate with agents, and we don't have time to go through things in details, but you can take a look at our documentation, you'll see more. For example, there's this one, which is looking at our fairly famous Daisy World example, famous in the sense that the model itself is famous, not that we made it famous. But this adds measurements.jl into the process and allows us to automatically get these sort of uncertainty values for this particular model. This is a integration of agents, dynamical systems, and differential equations, and black box optim to provide an integration, and this one as well, to provide a complete integration of a lake ecosystem and its dynamics, its stochasticity, and that is coupled directly to a governance system that tries to manage the lake state through some interventions. And so just having agent-based models is not necessary. You can have dynamical systems within your model, similar to the dynamical systems framework that NetLogo provides, but incredibly more powerful. So to sum up, I just wanted to go over a couple of things that are in the pipeline for our next steps. We're actively coding up more and more things into agents, and we have a very exciting roadmap. So this particular example you just saw there was an initial sort of part of our pathfinding integration. So those agents weren't actually doing anything other than trying to follow the shortest path to the goal where they are sitting right now. And this is being expanded as we speak by our Google Summer of Code student, Ayush, and he is doing an exceptional job to extend the pathfinding that we have for the moment in the grid space to be generalized to ND space, and also to be incorporated into the continuous space aspect of our system. On top of that, we have excellent 2D viewing capability at the moment, but not necessarily three-dimensional. So we want to look at that in the very near term, as well as actually allowing you to run models essentially in the cloud or online in general. So whilst our documentation provides running models and running examples, we don't have any interactivity there yet. And so using WGL Makey, we have a plan for that in the very near future. And then some things that are on the cards, but we can't promise anything straight away. These will take some time to develop. First thing we want to look at is tight integration with the ODD protocol. Now, if you're not familiar with agent-based models at all, the ODD protocol is it's trying to be a standardized way to describe what an agent-based model is and what it does. And these things are quite long-winded, and it's sometimes complicated to be able to fill out these sort of things. And with the Julia macro system, we really want to sort of try and provide a tight integration and try and actually generate a lot of this protocol for you. And then we have two things that ultimately fit together in some way or another, and that is property discovery. And so one generalized system here is the concept of causal discovery, which you can automatically identify aspects of your model and properties of your model that you didn't input into the system, but does sort of come out. And then finally, automatic PD discovery. Now, this is actually quite exciting. So the general concept here is that if you look at something like a reaction diffusion system in chemistry, you can model that using agent-based models, but that generally, when you want to simulate a couple of million molecules, that's going to take eons to calculate, and so you can't really have that precision, even though you understand the bottom-up dynamics of how this works. What you can do, or what you should be able to do, with integration with a lot of the SciML toolkits now, we should be able to use this concept of universal ODEs that the SciML team are working on, and the SIMD process to be able to capture various aspects of the agent-based model and its dynamics to actually generate a closed form solution of some subset of agent-based models. And so that's a very exciting process that's underway, but slowly but surely happening. So this is a very quick first look at Agents.jl, and I really encourage you to take a look at our documentation. It's fairly robust and fairly complete. So take a look, get started, get in contact with us. Thank you very much.